So in this video, part 2 of our section 6.5 logistic growth, we're going to actually solve a logistic growth differential equation, which is pretty involved. It would be quite unusual. I don't know if they've ever asked anybody on an AP exam to do this. It'll be more likely to answer the questions that we asked on the other video about just the nature of the differential equation rather than actually solving it. But that's not to say you won't be asked to do one on my test. So in 1985 and 1987, the Michigan Department of Natural Resources airlifted 61 moose from Canada to the Upper Peninsula. It was hoped that the population would reach a carrying capacity in about 25 years, with a growth rate given by this differential equation. dp dt is equal to 0.003 p times 1,000 minus p. According to the model, what is the carrying capacity? So again, what we do is we look at the part that is in that second parentheses, set it equal to 0 and solve, and that means our carrying capacity is going to be 1,000 moose. Now, the next thing we're going to try to do is actually solve this. Just a suggestion, oftentimes in AP questions or in questions that are just given to you, this will not be in this nice clean form that it is. And so what I would recommend is before you solve the differential equation, you simplify this as much as you can. By that I mean it might have been given to you as something like, say, 0.0001, and then that 3 would have been left off the p, and that 3 might have been brought inside as 3,000 minus 3p. So whatever the case, what I would recommend is factoring out whatever is in front of the p, leaving the negative sign, but everything else I would factor out. So in this case, factor that 3 out and bring it to join whatever that number is in front. This number is easy to deal with, as you may see when we do this differential equation, but leaving it in here makes things just more complicated. Just a suggestion. So here we go. To separate our variables, so we're going to divide the p and the 1,000 minus p to the other side. So this is going to look like 1 over p times 1,000 minus p dp. That constant 0.0003, we're going to leave that and multiply the differential dt to the other side. Now we're ready to integrate both sides. Now on the left side, you may see, hopefully, this is going to be our partial fraction integration technique that we're going to have to use. So we are going to think of that integral on the left as being a over p plus b over 1,000 minus p. And I'm going to say that's going to equal that 1 over p times 1,000 minus p. I'm going to slide the screen up a little bit. So then we're going to solve for the a and the b. So we're going to multiply through here by that common denominator of p times 1,000 minus p. So that's going to give us a times the 1,000 minus p plus b times the p. Guess I can just write that as bp. And that's going to equal the 1 on the other side of the equal sign. We're going to choose carefully selected values of p, say 0. That will give us 1,000. A is equal to 1. And so our A is going to be 1/1000th, or I'm going to write it as 0.001. Plugging in 1,000 for the P will give us 1,000. B is equal to 1, and so B is also going to be 0.001. So our integral has now become A, which is, I'm I'm going to call it 0.001 times 1 over p dp, plus we've got the b, which is 0.001, and that's 1 over 1,000 minus p, and that's going to equal, remember our other side of the equal sign is that 0.0003 dt. So we're going to get 0.001. This is going to become the natural log of p, plus now here we're doing a little u substitution in our head. So when the u is 1,000 minus p, the du is going to be a negative dp. So it's going to make that end up being a negative. So I'm going to call that a minus 0.001 times the natural log of 1,000 minus p, and that's going to be 0.0003 t plus, there's our constant of integration c. Now, this next step is really critical. This is not the order that we want in the subtraction, because ultimately we're going to try to condense these logarithms into a single logarithm, but we don't want to have p over 1,000 minus p, because then we can't split up the denominator. We do want 1,000 minus p over p, which we can separate. So I'm going to get rid of these 0.001s, and simultaneously I'm going to change the sign of this, the order of this subtraction, by multiplying by a negative 1,000. And that negative is a critical step, because it gets really, really tough to solve if you don't do that. So multiplying by the 1,000 is going to get rid of those 0.001s. The negative, multiplying by the negative, is going to switch the order of this. So it's going to be the natural log of 1,000 minus p minus the natural log of p. And that's going to be, and if we multiply by 1,000 on the other side, it's going to change, whoops, the negative 1,000 is going to make that a negative, and then it'll be a 0.3 t. And we haven't decided what the c is yet anyway, so we don't have to really worry about that being a positive or negative yet until we use our initial condition. Now this is an improvement, because now on the left side we can condense this logarithm into what we really want, which is 1,000 over p all over p equal to that negative 0.3 t plus c. I'm going to move the screen up a little bit here. So now we can exponentiate both sides and get rid of that logarithm, and it's going to be 1,000 minus p all over p, and on the other side we're going to call that c e to the negative 0.3 t. Now this is good news, because now on that left side, because our denominator is a single term, we can split that apart and call it 1,000 over p minus p over p, which is 1, is going to be that c e to the negative 0.3 t. Then we can add that 1 to the other side, so we're going to get 1,000 over p is equal to 1 plus c e to the negative 0.3 t. Now I'm going to take the reciprocal of both sides. So on the left side, because that's just a single fraction, we can just get p over 1,000. Now on the right side, because of that addition, we cannot take the reciprocal of each of those separately. So instead, it's going to be 1 over that whole thing. So we have 1 over 1 plus c e to the negative 3t. So I'm going to slide this up a little bit more. We can multiply by 1,000, and now we're getting there. So we've got 1,000 over 1 plus c e to the negative 0.3 t. Now we can use our initial condition that p of 0 is 61. So 61 is going to be 1,000 over 1 plus c, and then e to the 0 is just 1, so it's going to be just that 1 plus c. So we can multiply that 1 plus c to the other side, and we can divide by that. Do I want to do that? Divide by that 61, I think so. Let's go 1,000 over 61, and we can subtract our 1 from that, which is going to be a little bit messy here because that's 61 61st, which if I slide that up a little bit, I think that's going to be, whoops, that's going to be, let's see, um, 939 over 61, or if we just throw that in our calculator, that's going to be about 15.393 to 3 decimal places, which makes our population P of T 1,000, that's our carrying capacity, over 1 plus 15.393 e to the negative 0.3 t power. There we have it. That's a solution to a logistic growth curve, a logistic growth differential equation. Very good.